Welcome to this explainer. I am so thrilled to have you here today. When we talk about quantum computing, it is incredibly easy to get entirely lost in the abstraction. It often sounds like pure sci-fi, right? We hear talk of parallel realities, teleporting information, mind-bending algorithms. But today, we're going to ground all that science fiction into hard, physical reality. We are going to look at the actual physical atoms, the literal microscopic building blocks that make quantum computing possible. By the end of our time together, you're going to see exactly how physicists harness the fundamental laws of nature to build the ultimate computing machine.
Okay, let's dive into this. Here's our blueprint for today. We'll be looking at the foundations of the quantum world, orbitals in the periodic table, key elements of ion traps, isotopes, and the perfect qubit, and finally, fine structure and clock transitions. We're taking a journey from basic physics all the way up to cutting-edge engineering. Starting with Part 1, Foundations of the Quantum World, the Atomic Blueprint. To really appreciate the elegance of cutting-edge qubits, we first need to quickly revisit how early physicists actually mapped the atom itself. Let's race through the history here because it perfectly illustrates how our understanding evolved. It all kicks off in 1897 when J.J. Thomson discovers the electron. Fast forward to 1913 and Niels Bohr introduces a pretty radical idea. Electrons don't just fly around randomly, they exist in specific fixed orbits. Then, by the 1920s, brilliant minds like Heisenberg and Schrödinger established wave mechanics. They essentially proved that electrons behave like waves, not just tiny particles. And finally, in 1925, Pauli defined his famous exclusion principle. The big takeaway here is how every single one of these discoveries progressively built a set of strict, unbreakable rules that electrons absolutely must follow. And those strict rules bring us to the very definition of the word quantum. In the atomic world, electrons exist only in specific fixed energy orbits, or shells, around a nucleus. There is absolutely no existence in between. None. Because electrons act like waves, if an electron tried to exist between these designated orbits, its wave frequency wouldn't match the distance. It would mathematically and physically cancel itself out and just vanish. This strict here or there, but never in between rule is the foundational law of the quantum world. Moving right along to Part 2, orbitals and the periodic table, the rules of the game. So we've established these fixed orbits. Let's look at how these rules dictate the structure of literally every element in the universe. To keep all these electrons neatly organized, nature uses what we call quantum numbers. Honestly, think of this as a cosmic zip code for an electron. We have the principal number for the energy level, the azimuthal number for the subshell shape, the magnetic number for direction, and the spin number for the rotation. And here is exactly where Pauli's exclusion principle from earlier kicks in. No two electrons in an atom can have the exact same set of these four quantum numbers. It's a perfectly organized, highly regulated system. Now, what's incredibly fascinating is how these numbers translate into actual physical geometry. As we add more electrons to heavier elements, the shapes of these orbital subshells get wildly complex. They move from simple, elegant spheres in the s orbitals to dumbbell shapes in the p orbitals, to these four-leaf clovers in the d orbitals, and eventually to incredibly intricate, beautiful forms in the f orbitals. And those f orbitals, they are totally crucial for our story. If you look at the bottom of the periodic table, you'll find the f block. It's often pulled out entirely from the main grid. Elements down here, like ytterbium, are amazing anomalies. Because of the complex energy math, nature kind of throws a curveball. They actually start filling their inner F energy shells after they've already started filling their outer shells. This unique reverse ordering makes their atomic structure incredibly special, and it is exactly what quantum engineers are looking to exploit. That brings us perfectly to Part 3, key elements of ion traps, the chosen few. Out of the entire periodic table, modern quantum engineers have narrowed their focus down to a very specific group. When you consider elements like calcium, barium, and ytterbium, you're looking at really heavy, complex atoms. Because they are so massive, and because their inner shells are packed tightly in those complex d and f orbitals we just talked about, their outermost electrons are left somewhat isolated. This means they're perfectly positioned for engineers to hit them with lasers and manipulate their quantum states without disturbing the rest of the atom. It's brilliant. And the tech industry has definitely taken notice, placing massive, multi-billion-dollar bets on these exact atoms. Oxford University is relying on calcium. IonQ utilizes ytterbium and barium. Quantinuum and Oxford Ionics are deeply invested in barium. They're all using a sophisticated mix of highly calibrated lasers and microwaves to control these ions. But here's the catch. Simply picking a great element like barium isn't enough to build a stable computer when the stakes are this high. The rabbit hole goes a bit deeper. Part 4, Isotopes and the Perfect Qubit, the Secret Ingredient. To find the perfect qubit, the ultimate vessel for quantum information, we have to look past the electrons entirely. We actually have to look deep inside the nucleus itself. That secret ingredient lies in isotopes. Just as a quick refresher, an isotope is an atom of the same element, meaning it has the same number of protons and acts chemically identical. But it has a different number of neutrons. Sure, this changes the atom's mass, but far more importantly for quantum computing, it dictates a vital property called nuclear spin.
Let's use barium to see why this matters so much. If you take the isotope barium-138, its nuclear spin is exactly 0. Because of this, it literally cannot form complex internal energy layers. But if you look at barium-137, it has a nuclear spin of 3 halves. This specific spin interacts with the electron, creating 8 distinct, highly stable hyperfine states. Without the right nuclear spin from the right isotope, you absolutely cannot create the complex structures needed for stable quantum memory. So why do we care so intensely about stability? Well, let me introduce you to the ultimate enemy, the Zeeman effect. In the quantum realm, environmental noise is a relentless villain. The Zeeman effect happens when external magnetic fields, from the Earth, from surrounding electronics, from practically anything, destabilize and shift the energy levels of your atom. If your energy levels shift unpredictably, your qubit loses its data and your whole quantum computer crashes. Defeating the Zeeman effect is literally the holy grail of ion trap engineering. Let's move to part 5 and see how this builds to a magnificent solution. Fine structure and clock transitions, ultimate control. We are now entering the most precise level of quantum engineering. Basically, we have 2 main ways to store information in an ion. The fine structure uses relativistic effects to split energy levels. It allows for incredibly fast operations using lasers, but unfortunately, it's highly vulnerable to that magnetic noise we just discussed. The hyperfine structure, on the other hand, which requires that specific nuclear spin from our isotope, splits energy via the magnetic interaction between the electron and the nucleus itself. It operates at microwave frequencies and boasts an extremely long coherence time. That means it holds on to information much, much longer without degrading. Let's quickly look at the math behind this stability for our hero isotope barium-137. Engineers calculate the total angular momentum, represented by the letter F. You simply add the nuclear spin to the electron spin. So for barium-137, that's 3 halves plus 1 half, giving us resulting F states of 1 and 2. And this isn't just theoretical math. This calculation gives engineers the exact discrete energy states they need to confidently designate a 0 and a 1 in a quantum computer. And this brilliantly illustrates the ultimate defense mechanism, the clock transition. A clock transition is a highly specific leap between 2 of those hyperfine states we just calculated. What makes it so incredibly special is that at this specific transition point, the first derivative of the frequency response to an external magnetic field is 0. In plain English, it acts like an invisible protective shield. When operating at a clock transition, the qubit becomes practically immune to the Zeeman effect and surrounding magnetic noise. It's a game changer. So let's tie this entire atomic journey together. Why is a barium-137 ion an ideal quantum building block? Well, first, it's a specific isotope with the precise nuclear spin needed to create a stable hyperfine structure. Second, that structure allows engineers to exploit a clock transition, effectively shielding the quantum memory from environmental magnetic noise. And finally, by stripping away an electron to make it an ion, it gains an electrical charge. That allows us to physically grab it and suspend it midair inside an electromagnetic trap. Layer by layer, rule by rule, nature gives us the perfect qubit. We've journeyed all the way from the earliest fuzzy models of the atom to isolating a single, highly specific isotope, stripping its electrons and manipulating its internal nuclear spin to shield it from the magnetic noise of the universe itself. It really is a breathtaking feat of human engineering. And it leaves us with one final thought to ponder. If we now possess absolute atomic-level control over individual ions, what is the ultimate limit of what we can compute? Thank you so much for joining me on this explainer. Keep learning and stay curious.